Welcome to System and Devices 1, Week 6 review, what you should know at the end of the week. Okay, we're continuing to look at our instruction set for our processor. So we're looking at the machine level instructions that our Simple CPU version 1A supports. And for this first implementation, we have a very limited instruction set. So we have 4 immediate, 4 absolute, and 3 direct addressing mode instructions. So in this week's lab, we're looking at CPU sim to investigate how these machine level instructions are broken down into micro instructions, that is the internal steps that actually implement our machine level instructions functionality. So make sure you're happy with the RTL syntax as discussed previously, how this describes what each instruction does do, and also make sure you're happy about the bit fields used in each instruction. So how we represent our opcode and how we represent our operands, be they immediate values, so constants, or absolute values, addresses. So a key element of this week's lecture is the investigation of actually how the hardware elements that we've been building up over this series of labs are controlled within the processor to implement this desired functionality. And in the lecture we had quite a bit of discussion about how these control signals were generated. And a key thing to remember here that each row in this spreadsheet is a micro instruction. It's the state of the control signals within the processor for a specific phase of a machine level's instructions execution. So do make sure you're happy about what this table is actually telling you. We then had a look at the logic that will implement that truth table in that spreadsheet, and that's what you can see here. So first of all, we had our ring counter, and obviously the processor needs to know what state it's in. Is it in a fetch, decode, or execute phase? And that is represented as a 1 hot value with our 1-1 indicating our current active state. Then we have to work out what instruction we're executing, and again that is based on our simple 1 hot decoder as we saw in the encoder decoder labs. So we take our 4-bit opcode, pass it into our standard 1 hot decoder, and we'll generate a 1 hot representation indicating the current instruction that needs to be processed. And if we combine all those things together, we can finally implement the control logic that will generate the control signals to control the hardware in our system to implement our processor's functionality. We then had a look at how we will actually implement the memory of our system. One of the key ones was to move to byte addressable memory so that we maximized our memory usage. We didn't waste any space when we were storing data out into external memory. Again, we don't want to sacrifice the advantages of having a word addressable memory when we fetch an instruction. So we can read a 16-bit instruction within one memory transaction, and we can read and write to individual bytes within one memory transaction. As always, that has an impact on our system, so do make sure you're happy about byte addressable memory, endiness, big endian, little endian, and the impact that has on our addresses that we use within our programs. Finally, just to check that you were happy with all these ideas and concepts, introduce the idea of self-modifying code and a Wheeler jump. So this is the final test to see if you understand assembly language program. Can you understand what's happening within this program? How we can implement a subroutine call using self-modify code. And obviously, just to re-emphasize, self-modifying code is not a good programming technique, and we will be replacing it later in the Simple CPU version 1D with the call and return instructions. But it is a very good example to test out these fundamental ideas. Do you understand what the difference is, if any, between instructions and data? Okay, moving on to this week's lab. So we looked at CPU sim, where we can build a simulation model of our simple CPU processor, and we're going to do that using an RTL description. It's a standard way of representing how the machine operates, how instructions update the various storage elements within the processor. So what we're going to do is going to take our block level diagram and simplify it down into this register transfer level description. So in an RTL description, you only look at the memory elements from your system, so the program counter, the instruction register, our data register, or external memory. The internal operation of our ALU, the multiplexers, and other combinatorial logic blocks are just simply kind of removed, and we just assume that they are happening, and that simplifies the model greatly. So in the first part of the lab, we build our simulation model. A couple of compromises had to be made to fit into the way CPU sim implements its simulation models. This involves the addition of these fake registers, the address and the data. In CPU sim, all information has to come from a register, but in the simple CPU that's not the case. You can see here we have our address multiplexer and our data multiplexer are providing information. Therefore, within CPU sim, where you see the source specified as the address, then that is coming from the address multiplexer, and when you see it data, it's coming from this data multiplexer. But in CPU sim, they had to be described as registers, and obviously they're not in the simple CPU, they're just multiplexers. Hopefully that small modification was not too confusing, but in task 1 you build this simulation model, and then you can build the instruction set. So in task 2, this is the main point of this lab. So what I wanted to do was to make sure you're happy about the relationship between the assembly language syntax that you'll be using within your program, the internal machine code representation in terms of its bit fields, and then the link from this machine level instruction to the micro instructions that actually implement that functionality within the processor. So there's a little bit of discussion about different instruction formats, so 0 operand, 1, 2, 3 and 3+ type formats, and they all have their advantages and disadvantages. In general, the more operands you specify in the instruction, the more functionality you can describe, so helping to reduce the size of your program. For this lab, we're only going to look at the immediate addressing mode. So you can see here that these are 1 operand instructions. So you have your opcode and you have 1 operand, and the operand will be an immediate value, i.e. a constant stored within the instruction register that can be accessed immediately. We do not have to go out and read memory to get to the operand. So you can see here for the simple CPU, we are using these particular bit fields. So for the opcode, in this case move, we're using 4 bits in the top nibble, the top 4 bits, and we're giving it the value 0. Why the value 0? Well, no good reason. You can, as long as each opcode has a unique value, you can assign any particular value. In general, that's true, but sometimes we do select particular values to help minimize the instruction decode logic. For our operand, the value 12 in this case, again we have to assign it a certain number of bits to represent its value, in this case the lower 8 bits specifying that immediate value. Now hopefully you can see here that the size of your opcode field is determined by how many instructions you have. For the simple CPU we've only got 11, so 4 bits is ample. Again, the size of your operand is defined by the size of the values you want to process. And again, we're going to stick with small values for the moment, as 8-bit values are perfectly fine for what we're doing at present. So within CPU Sim, we have to define those bit fields that we'll be using to build our machine level instructions. So then we can drag and drop these bit fields into this GUI here to build up our machine level instructions, defining its structure. But then we need to define the micro instructions that will be used in the execution phase to implement that functionality. So the micro instruction involves in moving that immediate value into the accumulator, as you can see here. And that is also true for each phase of the instructions execution. So we have to define the micro instructions, the internal steps that will be performed for the fetch phase, for the decode phase. And once you've done that, you've built your processor. So again, another key kind of milestone, make sure you're happy about how this assembly language syntax is represented in a machine code instruction, so how it's broken down into its bit fields, and then how within the processor that machine level instruction is broken down into a series of steps, a series of micro instructions that actually implement the desired functionality. And when you've done that, you can run your simulation of the processor running the program within CPU Sim. And it's a very nice environment to kind of examine what's happening at each stage. So what you've got here is your registers that will be updated, your assembly language program, your instruction memory, as we can see here with the machine code loaded in. And you can step through either at the machine instruction level or at the micro instruction level to see what's happening in that machine and see how these internal registers are updated at each step. So fingers crossed, touch wood, at this stage you understand how your immediate instructions are built up in terms of the machine code, how they are actually executed within the processor, and you can then implement all these other instructions that are of a similar format. And next week we'll be using CPU Sim again to implement the other instructions. So our absolute addressing mode instructions and our direct addressing mode instructions, our control instructions. Finally, as always, we have this week's exercise sheet. I do confess some of the questions are a little bit on the tricky side, so there's a few little tricks in question kind of 4 and 5. I would hope that everyone could answer the questions in their basic form, but when they ask for the kind of extra functionality, so can you implement this code in 4 instructions, that may be a little bit more tricky and you might need a little bit of assistance with that one. As always, we're continuing our development of our robot cockroach, but I do confess now that we're implementing these different state machines that this material is quite similar now as we build our different state machines. But the key reason why I included this in this week's exercise is I wanted to show that more formal implementation of a state machine from your state diagram. So you describe the robot's behavior as this state diagram, and obviously you could realize that in software, but equally you can realize that in hardware. So we're going to implement it as a kind of classical Moore state machine. So we'll have our state register, some input forming logic and output forming logic. Those are described by their associated truth tables. We can then convert them into Boolean algebra expressions, minimize them, and then implement them as a schematic. So here we have our state register, our output forming logic, and our input forming logic. And the main point to note here is that this output forming logic is very similar to our decode logic that we'll be using in the simple CPU. So kind of transferable skills. Okay, finally, in this week's workshop exercise sheet, we have our example exam questions. So this week you should be able to answer question 2. So what we'll be doing at the end of each exercise sheet, we'll be implementing a solution for the example exam, but we'll be implementing it on the Simple CPU version 1A, because obviously we haven't got to the Simple CPU version 1D yet. That's the process you'll be using in the open assessment. So there's a slight change. So in the example exam, you are asked to build a 16-bit rotate, but obviously the Simple CPU version 1A is an 8-bit machine, so here I just modified it so we have got an 8-bit rotate component. So I'd hope everybody could basically create a schematic, create the symbol, implement this rotate functionality. It's exactly the same as we sort of saw in the encoder decoder lab. All you need is buffers to rewire the input to output such that you move the lower 7 bits up one position, and the 8th bit, bit 7, that you would lose will be shuffled back round to the least significant bit position to implement your rotate functionality. So do have a go at that one, and again, if you're not happy about that, give me a shout in the Q&As and I can draw you the circuit and talk you through it. Okay, I think that's where I'll leave it for this week. I'll see you in the next lecture.